three different methods for solving kinetics problems. We have learned Newtonian kinetics. So that's Newton's laws. He had 3 laws, and that's chapter 13. We've also done work and energy. And subset of that is conservation of energy. That is chapter 14. And then finally, we learned impulse and momentum. That was chapter 15. And also conservation of momentum is included under that. Now, we talk about energy and forces. There are different kinds of these. So energy can be stored or dissipated. So if it's stored, that is conservative forces. And it is path independent. So that means that the energy, if energy is conserved with conservative forces and stored, then it doesn't matter what happens in between states 1 and state 2. Because all that's happening is that the energy is changing form. And so the actual amount of energy is not going to change. And so it doesn't matter how you get from state 1 to state 2, as long as you get there conservatively. So examples of this conservative energy storage, it can be done in a mass, which is kinetic energy. It can also be stored in a spring or gravity. Which is potential energy. Or there can be a push or a pull, which is the conservative work. Also, energy can be dissipated. So if energy is dissipated, then it's lost. And examples of this are friction. This is the most common. Also damping, which is like friction that's proportional to velocity. And then drag, so resistance from a fluid. And all of these contribute to the non-conservative work, which is less than 0. Whereas conservative work is greater than 0. And so now we're going to make a chart of different types of energy and forces and what their formulas are. So we'll have the type, we'll have the force, and then we'll have the energy or the work. We remember that work equals integral of F dot ds. So it's a force moving across a distance is what causes work. So first is gravity. So gravitational force is mg, and the gravitational potential energy is mgh. So you can see mg is the force, h is the distance, so then the energy, mgh. Next is a spring. The spring force from Hooke's law is K times S, where S is the distance that the spring stretches. We've also seen that as K times L minus L initial. So then that energy is 1/2 k s squared, integral of force over distance. Then in a mass, we have kinetic energy. So force from a mass moving is going to be ma, and its energy is 1/2 mv squared. So then conservative work from a push or a pull, that is just P given in the problem. So for a constant force, the work done is just P times S. If the force were not constant, if it were a function of S, you'd have to integrate. And then finally with friction, we know the friction force is going to be the coefficient times the normal force. And this is always going to be, for work that's done by friction, the dissipated, you'll always use the kinetic friction because the object's got to be moving across a distance for any kind of, for the dissipation to happen. So you use mu k. So then that is going to be mu k times n times s, that pushing distance. Now, to review the problem solving procedure. Now, the first step is always draw the diagram. So this is going to be a free body diagram for the Newtonian kinetics or the work and energy. And it's just kind of going to be a picture of the problem for the impulse and momentum. Then the next is assign a coordinate frame. Generally, we put x in the direction of motion and y perpendicular to it. For Newtonian kinetics, then x has to follow the rope. So if you have multiple objects that are connected by a rope, then make sure that your coordinate frame moves consistently from one to the next one. For work and energy, usually y goes vertical and x goes to the side. And then for impulse and momentum, x goes along the line of impact and y goes along the plane of contact. The third step is write the equations. So each one of these three approaches has its own set of equations. You just need to be able to figure out which equations to use. And you can do that based on the variables in the problem and what happens in the problem. Sometimes it will take more than one equation, and you'll also have to do the static check. So equations are going to be one of those three types. And then 4 is solve for whatever the problem asks you for. Now, the tricky part is knowing which equations to use when. So for the homework, that was easy to know which equations to use because we had one homework on each chapter. The exam will cover all 3 chapters. And so you have to be able to figure out when do you apply which types of equations. Let's make a chart that will help with that. First thing we're going to do when we start is check if there's a collision. Then if there is a collision, we need to check if there's an impulse. So remember that impulse is the F delta T. So then if there is an impulse, then we'll use the impulse and momentum formula. Which is that m v1 plus interval of f dt equals m v2. If the force is constant, which often happens, then you have the f delta t. Now, if there's no impulse, then we know to use conservation of momentum. So momentum is conserved when the f dt is 0. So either force is 0 or dt is 0 or both. So for that, we have two equations. ma va1 plus mb v1 equals ma va2 plus mb v2. This one's conservation of momentum. And then the other equation we have is the coefficient of restitution. E equals negative va2 minus vb2 over va1 minus vb1. And we remember that E can either be 0 for a plastic collision, when the objects stick together. It can be 1 for an elastic collision, which is when energy is conserved, or if it's something in between that's inelastic. So there's rebound, but it's not a great rebound. All right, so then what if there was not a collision? What are we going to do? So if there's not a collision, then we check what motion variables are involved in the problem. If acceleration is involved, then we know to use Newton's laws. So sum of the forces equals mass times acceleration. Remember that that's a vector, so you write it for each direction. And usually it'll be something like blocks are on a plane, solve for acceleration of the blocks and tension in the rope. Could also just ask you to like solve for the force on whatever. So then it's not acceleration. Let's say if it is position or velocity, then we have to check if there's external forces. If there are external forces, then we're going to use work and energy. So energy at 1 plus work from 1 to 2 equals energy at 2. Remember, energy is a scalar, so it just depends on whether it's positive or negative. then we remember to get the work, it's going to equal integral of F dot ds. And work non-conservative is less than 0, so it's negative. Work conservative is greater than 0. So if something's pushing, then we'll have that greater than 0. If it's friction, we'll have the less than 0. Now, if there are not external forces, then conservation of energy is the correct approach. In that situation, energy at 1 equals energy at 2. So you just figure out potential and kinetic, plug those in. And then the final tricky part, if we have a collision, but it is an elastic collision, we can also use conservation of energy. So sometimes you will need more than one equation to solve a problem. So in those situations, then you need to recognize whether or not if energy is conserved, then you can use that one as your extra equation. Also, you might just need to end up doing it equations for x and y directions both or something, and that's how you will get the ones you need. Or you may realize that there are too many variables that you don't know. For example, if you're trying to do work and energy and you realize that you don't know the friction force, well, then you'll need to use Newton's laws to figure out the normal force and the friction force in order to then complete the work and energy.